My thesis title is Using Machine Learning to Classify and Predict Movies. I'm Hu Yuting. Let me introduce. The table of contents has 6 sections. Introduction, research background. Film genre classification is challenging due to multi-label complexity and large-scale data. Traditional methods have difficulty in handling the rich thematic features in port synopsis. Advanced in machine learning, especially deep learning models such as LSTM, enhance classification by capturing test details. In this paper, we compare multiple models to evaluate a multi-label classification performance based on IMDb dataset. Problem statement. The core problem of this research is how to solve the difficulty problem of multi-label classification of film genres. Research objectives. The aim of this study is to achieve automatic multi-label classification of film genres based on the IMDb film dataset using machine learning and deep learning approaches. Building machine learning and deep learning models for automatic multi-label classification of IMDb film summaries. Compare and test difficult models and classifying both common and film genres. Scope of research. This study uses models like LRF, NBDT, and LSTM to compare multi-label classification. It focuses on test feature extraction, model training, and performance compare using accuracy and FE scores. Outline. This study has 7 chapters. Data exploration, data obtained, data from Kaggle website for film genre prediction. 2 datasets are included. See the code shown. Data table structure and variable interpretation. IMDb film dataset structure specification containing title, overview, genre ideas, and genre names. See the code shown. Variable uniqueness and multi-label analysis. The title ensures that each film is unique. The genre names field shows that a film may have more than one category. For a total of 18 genres, the multi-tag structure increases the complexity and enriches the tag relationship. The overlook text is also divided and unique to ensure the diversity of model inputs. See the code shown. Distribution and visualization of category labels. We count how often 18 more types appear and find that popular types like drama and comedy have many symbols. Using pandas and counters, we draw bar chart to show this. See the code shown. Basic statistic analysis of data. The number of labels for each film is content stored in a new field name labels and statistic information. The results show that both single label and multi-label films are distributed with an average of 2 or 3 labels per film, reflecting content diversity. Visualization of the distribution of the number of labels through histograms show that most of the moves have 2 or 3 labels, which is an important guidance for model design. Data pre-processing, basic statistical analysis of data. change all text to lowercase to avoid treating. Use regex to remove punctuation and special symbols. Split sentences into words, remove analyze words, join clean words. Multi-label data binarization tools were used to implement binarization on multi-label data. TF-IDF feature extraction. Setting max feature equal 5,000 limits the vocabulary dimension and reduce noise. Relationship between work. The data is supplied by 18% training and 20% testing. LSTM model data preparation. This reduces model size and noise, focusing on core words and improving classification. Rare words are treated as OV and may be ignored unless marked. Setting an OV tool helps handle unknown words. Methodology, model construction, flowchart or methodology. LR use one-way list to handle multi-label tests. NB works well for test classification. DT splits data by features step by step. RF use many decision trees to reduce overfitting and improve stability. LSTM is a neural network for sequences data that remembers context. Results and discussion, model evaluation, uh, confusion matrix. Confusion matrix shows models prediction for each label. Accuracy measures correct predictions little but can mislead in multi-label tests as frequent label dominate. FE scores can best precise and recall key for multi-label evaluation. Prediction results and comparisons. The LSTM model significantly outperforms traditional machine learning models in terms of weighted accuracy 0.54 and macro FE score 0.44. It is not only good at multi-label prediction, but also better at identify nature types. Summary of the champion model. This study shows LSTM is the best model for multi-label classification. Conclusion and outlook. Limitation. The dataset has some limitations. Limitations future representation. Limitation evaluation index. Recommendation: collect more diverse data and use simple methods to balance the distribution of labels. Combine structural attributes and test features to improve model representation. Try advanced deep learning models such as Transform and BERT to enhance semantic understanding. Focus on model use in real applications. Reflection and summary. A deep understanding of the importance of multi-label classification tests. LSTM has superior performance, but still has limitations. Thank you.